Okay, thank you for giving me the platform once again. The title of my talk today is Exposing Basement Terrain of the North Australian Craton. So this talk is basically a summary of the paper that we published in 8th Science Review. That's myself, Peter Bates, and Robert Ahmet. And again, it's also a chapter in my thesis, Basement Architecture of the North Australian Craton. So in the thesis, this presentation, it's like it's it, it provides the background review of my thesis itself. So that's the brief background about the presentation. So it will just be a brief talk of the thesis chapter and the paper that we published in 8th Science Review. So that's the area of the review. So the area in red, that's what the review covered. And of particular interest is the interior of the North Australian Craton. So the whole of that is the North Australian Craton. And in red, that's what the review covered. In other words, that's what the talk is going to represent. And of interest will be the inside or the interior of the Craton. So just a brief introduction. There's little knowledge or there's little that is known about the interior of the North Australian Craton. And the main reason for that is because much of the interior is covered by the basins, and these basins, they have concealed the pre-1800 basement rocks. In other words, the other rocks or the basement rocks are only exposed in some selected areas of the North Australian Craton. So these are areas like the Litchfield, Horse Creek, Arion Province, the Mount Isa, Marthe, and some section of Alam. So these are the areas where we have basement rocks. That is the rocks which are older than 1800. That's where they are exposed. But the rest of it, and maybe the Tennant Creek. And the rest, we don't have exposure of those rocks. And the reason being because much of that is covered by the basins. And because of that, there is quite a disconnect. It's not easy to connect the dots between these exposed terrains because much of the interior, we don't see it. And because much of the interior is not exposed, it's very difficult to connect the provinces. And again, it's very difficult to understand how, if at all, these exposed terrains were amalgamated at some point. So we can't know all that because much of the interior is covered by the sediment. So this review is trying to see if we can get information from the exposed terrains and use that information to determine what lies beneath the area which is not exposed. That's the interior of the Craton. There are a number of models that has been introduced trying to explain the evolution of the North Australian Craton, and one of them is that of Peter Bates and others in 2016. And for these, they are saying that the North Australian Craton evolved with the amalgamation of cratonic blocks or continental blocks onto the Proto-North Australian Craton, which is the interior of the Craton. And there are other models which suggest that maybe there are different cratonic or continental blocks that are amalgamated along different or various sutures. And that is an example of RE 2014. And when you look at all these, we're going to see that the fact that we have contrasting models, different models talking about the North Australian Craton, just tells us how complex it is to understand, particularly the interior of the Craton. So this review is just about trying if we can get information of the current data that we have and see if we can use that data to understand what the interior is like. So the aim of the synthesis, as I just said, was to see if we can address the internal architecture of the North Australian Craton. And how do we do that? By looking at the basement exposures, particularly in areas like Horse Creek, Litchfield, the Tanami, Tennant Creek. So all those exposed rocks which are older than 1800, wanted to see if they can give us a clue of what is the basement in the interior. As I said, the interior is much more covered by the sediments. The other thing, which is the aim of this synthesis or the review that I had, was to identify major cluster boundaries in the interior of the North Australian Craton, as well as along the edges of the Craton. And what approach did we take? So it was a holistic approach. I just had to consider all the data set that could give us the information, and of particular interest, we are looking at the geological information. And along these lines, I looked at the basin and tectonic evolution, looked at geochronology, and we also looked at geoengineers chemistry to see if we can get some information from all that. We also had a review of the uranium read inherited zircon data of, zircon data with ages older than 1900. And again, we also looked at the neodymium geochemical data for pre-1800 magmatic rocks to map the basement and determine cluster boundaries. Why we focus on the pre-1800 basement rocks? Because we considered that all the rocks which are older than 1800, they form the basement, because most of the basins are younger than 1800. So that's why our focus was to look at all those rocks which are older than 1800. And why did I take much interest in the North Australian Craton? So the North Australian Craton is one of those provinces that is very rich in mineral resources. And the fact that we don't have exposure of much of the interior for the basement rocks, we only have basement rocks in the Tennant Creek here and part of the Murphy region, and the rest we have younger rocks. The fact that we don't have those basement rocks in the interior, it means if we know or we have an idea of the basement architecture, it will help us in the search for these mineralization into the interior. So we can extend our search for these minerals that we see in the exposed rock into the interior if we know or understand the basement architecture of the interior of the North Australian Craton. The other thing is the North Australian Craton, it's a significant element. It's part of the building block of the ancient Oceanic continent. So it's part of the proto-Ocean continent. So the other elements being the West Ocean element or the West Ocean Craton, the other element being the South Ocean element or the South Ocean Craton. So if we add all these together, they will give us, or they form, the ancient Ocean continent. So that's the other reason why we had to focus on the North Australian Craton. The other thing is the North Australian Craton has always been part of those supercontinent reconstructions. So it's been linked with Laurentia or North China Craton. So that's why it's important to understand the basement architecture of the North Australian Craton. So our review wanted to see if we can use the data that we have to infer or to see if we can understand the interior of the Craton, which I said is covered by the sediments. So what we did was to look at some of the similarities that we could get from the various exposed blocks, and again also look at some of the differences. In terms of the similarities, we noticed that there is a dominance for 1870 to 1840 magmatic rocks. So these are rocks which are like biotite, hornblende, bearing granitoids, and these granites are very common in the North Australian Craton, and we see them in all the exposed blocks. For example, in the Montisa blocks, we see them. In the Murphy blocks, we also see them. We see them in the Tennant Creek. They are also there in the Pine Creek, Horse Creek. They're also there, except maybe in the Tanami. So that similarity tells us one thing, that perhaps within this age bracket, maybe these terranes that we see as separate because they are very much far apart, separated by the basins, might have been together at some point. Another thing which is of interest is we have these terranes which are exposed, and we're seeing that in these exposed terranes, we have similar magmatic rocks in this age bracket, which is 1870 to 1840. But we also have similar rocks hidden beneath the basins. And a very good example is in East Tennant Creek here. So in East Tennant Creek, they intersected some magmatic rocks, which are of the same age as these rocks which are exposed in Mount Isa and the rest of these exposed terranes. So these intersected magmatic rocks are of the same age with the rocks in the Murphy block, same age with the rocks in the Tennant Creek block. And that gives us a clue that perhaps the whole of these might be the same. So according to the interpretation by Clark 2022, they are saying that maybe these rocks are part of the same magmatic event that formed the rocks in the Murphy block, and again, the rocks in the Tennant Creek block. So we can see that by just looking at this example, even though this section is hidden beneath the sediments, but we still see the rocks intersected in drill holes, which have the same edges as the rocks which are exposed in the Murphy block here and in the Tennant Creek block here. Another similarity that we also observed is the granite logs that we identify to be similar. They also have the same evolution path. Most of them are less radiogenic, as evidenced by epsilon neodymium values of minus 1.29 to minus 4.69. And these granites, again, they have almost similar model edges. So if we look at the model edges pattern here, we'll see that most of them range between 2.4 around here to somewhere around 2.6. So that's where we see the model edges of these granites is ranging. And another thing is they also have uranium lead inherited edges, which are older, much older, between 1900 and 3200 MA. And if you consider all this, and together with these negative epsilon neodymium values, we'll see that these rocks are interpreted to be products of recycling. So there isn't evidence that there was mantle-derived magma involved in the formation of these rocks. So most of them are a recycling of the crystal-derived rocks. So that's simply that. And when we also look further at the trace element geochemistry of these rocks, we see that most of these rocks that we've talked about, for example, the paperback supersuite, so this type of granite rocks and then again, we also have these types of granite rocks. All these, we'll see that most of them, they have depleted strontium as a trace element. So we can see from that. And this is different from the Douglas suit, which I'm going to elaborate later. So this similarity that we're seeing here is telling us that these rocks are derived from shallow depth. Another thing that we also looked like in the review was to look at the uranium lead inherited zircon edge pattern. And a striking thing that we observed is that most of these blocks, for example, the Pine Creek, Tennant Creek, Mount Isa, and Alam block, they have a similar pattern. And we see that pattern after 2600, that is between 1800 and 2600, we see that the pattern of inherited zircon edges looks the same. And that is different from the pattern that we observe in the Horse Creek, and again, the pattern that we observe in the Tanami. Another similarity that we also observed between the various blocks, it's about the sedimentary deposition. So before the orogenesis, so from this diagram, we'll see that around between 1850 and 1870, most of these terranes or blocks, Mount Isa, for example, Murphy, Tanami, Tennant Creek, Alam, Pine Creek, and Horse Creek, most of them, they experienced orogenesis. So that's between 1850 and 1870. Just before that, most of them, except maybe a few, like maybe Alam Block, they had similar deep water sedimentation, turbidites. And if we look at we analyze the detritus population for those turbidites, we'll see that they had some striking observation. For example, most of them, they had a dominant peak at 1900, between 1900 and 1865, and another secondary peak at 2500. So we'll look at the Murphy metamorphics, all these other turbidites, they have the same pattern, except the Grinder formation in Alam Block. Another similarity that we observed is just before orogenesis, as I said, most of the terrains in the North Australian Craton experienced deep water sedimentation. And then after orogenesis, there was that transition from deep water sedimentation to shallow water sedimentation. But in Alam Block, there was still deep water sedimentation taking place. That tells us something. Perhaps maybe Alam Block was slightly different from the rest of NAC at this point in time. Another thing that we also looked at was to look at some of the extensional structures that have been reported in literature. And what we noted was there was this similarity in the extensional structures in NAC between 2050 and 1870. That's this picture. And when we look at this, we'll see that most of the trend was the same. In Tennant Creek, we have those northwest trending structures, and similar northwest trending structures are also observed in the Pine Creek. We also have similar trend in the Tanami. And again, we're also looking at another trend, which is northeast for the transfer structures. And the fact that we have those similarities in terms of the structures tells us perhaps the basement might have been the same basement on which those structures are on. So that's another thing that we also observed. In terms of the differences that we observed between the NAC terranes or between various NAC blocks, one thing that we observed is that we have a distinct type of magmatism in some NAC terranes. For example, the Douglas Soot that we have in the Horse Creek. And this type of magmatism is different from the magmatism that we observed across NAC in that it is isotopically radiogenic, which tells us that it has some input from the mantle, which is unlike from what we have seen in the other blocks in NAC. So that's that. So most of these magmatism from the Douglas Soot, we see that it's isotopically radiogenic, telling us that it has some input from the mantle, which is unlike the magmatism that we just looked at earlier. And in terms of the primitive mantle normalized plots that we got for those granites, we'll see that for the Douglas Soot, it is undepleted in strontium, which is unlike the rest of NAC, which is depleted in strontium. So we can see from here. And what does this tell us? It tells us that the Douglas Soot was formed at a deeper crust, which is unlike the rest of NAC, which were formed under shallow crust. And the interpretation that we've got from the literature is that most of these granites were a recycling from other class of material, which is unlike the dugosute, which is interpreted in the context of subduction. So we can see that subduction magmatism in the North Australian Craton is restricted to the Horse Creek here. And we can also see the same during 1850 to 1800 in the Horse Creek again, we see that kind of magmatism. And this magmatism is very different from what we have just seen in the other Craton, in the other blocks of NAC. So what does that tell us? One, we are saying that the dugosute has undepleted strontium, and that reflects the depth at which it was formed, which is deep crust, and its interpretation, it's interpreted in the context of subduction. And what that means is the Horse Creek is different from the rest of the blocks that I mentioned earlier. The other thing that we also looked at, look at the differences in terms of sedimentation. Most of NAC experienced deep water sedimentation just before orogenesis. That's this period, 1900 to 1850. But after that, 1850 to 1800, the rest of NAC experienced shallow water sedimentation. But that was not the case with Aram Block, which at this point was experiencing deep water sedimentation. And when we look at the Tritozircon population of the sediments at this time in Aram Block, we'll see that there's a different from the rest of NAC in the sense that much of NAC, the turbidites had a major peak at 1900, which we don't see in the Aram Block here. And the other thing is we'll see the major peak in the Aram Block between 2000 and 2200, which is not very conspicuous in the rest of NAC. So what does that tell us? Perhaps during this period, the Aram Block might not have been connected to the NAC. The other difference that we observed is in terms of deformation. So crustal shortening initiated area in the western Horse Creek, Pine Creek, and Mount Isa Block. So if we look at this diagram, we'll see that deformation between 1850 and 1870 affected much of NAC, but it initiated area in the western zone here, and again area in the Pine Creek, and again area in the Mount Isa Block here. But it was much later in the Tanami as well as Tennant Creek. The other differences that we also noted across NAC was in terms of metamorphism. So we saw that high-grade metamorphism normally is found along the edges of the Craton. So we find high-grade metamorphism in Horse Creek, some sections of Pine Creek, and we also find that in Aram Block and as well as in the Mount Isa Block. But in the interior, Tennant Creek, Murphy Block, we see that there was green schist or low-grade metamorphism. And what does that tell us? Perhaps this pattern is trying to suggest that maybe tectonism at this point in time was focused along the edges and not in the interior of NAC. And then the question is, are there some cluster boundaries? Are there terrain boundaries in the interior of NAC? By considering what I've just talked about, we see that there is that similar pattern in some NAC blocks in terms of the inherited zircon edges after 2600. We also looked at the granites or granitic rocks, which are biotite hornblende bearing aged between 1870 and 1840. We see that they have the same chemistry, they have the same age. But again, we also looked at the turbidite deposition, which took place just before orogenesis and within the same age bracket. We also looked at some extension structures, which we also see that they are similar, telling us perhaps the basement on which those structures are resting on must be the same. So by considering all these, our interpretation is that perhaps NAC was unified as early as Neoproterozoic, maybe as early as 2600, and maybe between early Proterozoic, NAC was unified. We can't determine the boundaries within the interior of NAC using the information or using the data that we had. So what it means is perhaps this interior of NAC, based on the information which I've just presented, was intact during that period. There isn't any evidence that we could get from the literature that suggests that maybe there were different terranes in the interior. In conclusion, what we got from the review is that crustal boundaries exist along the edges of NAC. And again, we also saw that similar geochemical, geochronological, and isotopic characteristics of 1870 to 1840 biotite hornblende bearing granites tells us that maybe NAC share that early Proterozoic or Paleoproterozoic history. And again, we also looked at some differences in terms of deformational styles. We looked at high-grade metamorphism along the edges, and in the interior, we saw that much of the interior that we have that low-grade or green schist metamorphism. But again, we also see that if we look at the deformational history, for example, when we look at the Pine Creek, we'll see that there are those differences in terms of metamorphism and deformation, where some other sections, like the Nimbua block, they have maybe that high strain metamorphism or deformation, which is contrary to the Litchfield domain. So those differences suggest that perhaps there are those boundaries within them, but we didn't get that evidence to show whether those boundaries extend into the interior of NAC. So the main thing that we could get from here is we have boundaries along the edges. We have similar geochemical characteristics of rocks in the interior. Some metamorphism in the interior shows that much of the interior is green schist and high grade along the edges. Similar pattern of crustal structures in the interior. And all that points to one thing, that perhaps the interior might have been the same using the data that we have during the period I've just mentioned. So that's the end of my talk.